Hey guys, today what we're going to do is get a little bit more into pH and talk a little bit more about strong acids, strong bases, weak bases. Like that's the thrust of today. For this part, we're going to focus primarily just on the pH scale and other P scales. So let's jump into it here. First off, remember that pH refers to the negative base 10 log of a hydrogen ion concentration. So as you think about it, you've got to remember how logarithms function. Essentially, what we're doing is we're uh, taking some power of 10 and we're relating that so that the power is emphasized. If you look right here, if I have a hydrogen concentration in a neutral solution, for example, I know that H plus is equivalent to 1 times 10 raised to the negative 7 power. So using that molarity, I plug that into my expression here, and we'll see that the negative logarithm of that value ends up becoming negative 7. The power here gets thrown in, and then we have our negative sign, so that changes it to a positive 7 power. So for all neutral solutions, we'd have a pH of 7. A couple things to emphasize as well. In the table below, you can see how we connect hydrogen to hydroxide ions, and then we've also thrown pH in there as well. Whenever you have an acidic solution, you see that the hydrogen concentration must be above 1 times 10 to the negative 7. Hydroxide must be below 1 times 10 to the negative 7. And that results in a pH less than 7. So here's our big connection. Acidic, pH less than 7. Our hydrogen concentration is more than 10 to the negative 7. The second connection that we want to make here is neutral solutions. They're going to have hydrogen of 10 to the negative 7, hydroxide also 10 to the negative 7. So these two concentrations must be equal to one another. You will have a pH value of 7 even as well. Final thing here is for all basic solutions, hydrogen is less than 10 to the negative 7, hydroxide is greater than 10 to the negative 7, and your pH will be above 7.0. Now what I'd like you to do is, just keeping this in mind, I want you to consider what could happen if I have an acid or a base, let's say, in very, very high concentrations. For example, hydrochloric acid in its stock form is roughly 37% acid. It comes out to being around a 12 molar solution. Well, if I were to plug in 12 using the negative log, what comes out of that is going to be a negative value. So if you ever do see a pH that is negative, it's less than 0, that means we have a molar concentration of hydrogen that's going to be greater than 1. Okay? So beyond just pH, we also have pOH and some additional P scales. Well, if pH refers to hydrogen, then pOH refers to hydroxide ions. So pOH is the negative log of the hydroxide ion. Another kind of interesting thing that we can get from this is using our relationship with Kw. Kw is the concentration, remember, of hydrogen ions multiplied by the concentration of hydroxide ions. Well, if I were to take the logarithm of both sides, I'd find that the negative logarithm of the Kw value would be equivalent to the negative logarithm of the hydrogen concentration. And when you do logarithms here, these multiplied values become split and added. So plus negative logarithm of our hydroxide ion concentration. Essentially what that means is negative log of H plus, that's pH, plus the negative log of OH minus, pOH, is equivalent to negative log of Kw, which is also sometimes referred to as pKw, and the value of that has to be 14. So pH plus pOH is equal to 14 under standard conditions. The next concept here, just give it a little bit of thought, is if our pOH is 3, what's the pH and is this acidic or basic? So stop and think about this and work it out in your head. Relating directly to what we said above, pH and pOH have to add up to 14. So we can say that 14 is equal to the pH plus the pOH we'll plug in, which is 3.0. Just subtract the 3, and you'll find that we have a pH value that's equal to 11.00. And if you got a pH, remember that is greater or less than 7, that's your ticket here, right? In this case, we're saying it's a pH greater than 7, so that means that it must have been a basic solution. Finally, we're going to talk about measuring pH. So measuring pH. We can measure pH in a number of ways. Typically, we'll have an electronic device that is going to give us a voltage that is generated based on how many ions are present, specifically hydrogen ions present in that solution. So we'll get a digital readout of the pH, which relates directly to the hydrogen ion concentration. Now, I'm going to get into another form outside of using these electronic devices. We also have indicators, colored solutions that change in the presence of acids and bases. So some of the common ones that you'll find are listed here. Methyl violet, thiamyl blue, methyl orange, methyl red, bromothiamyl blue, phenolphthalein, and alizarin yellow R. Notice that the color change windows relate to the specific pH range where they're sensitive. So all of these have a different range. We do have this interesting situation where thiamyl blue actually has multiple expressions. It has a red to a yellow, stays yellow in the middle, and then it can shift to a blue depending on the pH range. So choosing an appropriate indicator may help us as we're performing titration experiments, and we're going to get to that a little later. But I want you to think about this. If, in this first question, if you had a colorless solution that turns pink when you add phenolphthalein, what do we know about pH here? So we're going to identify here the phenolphthalein indicator. This is going to have its transition here somewhere in the 8 to 10 pH range. Well, it's colorless at pHs below 8, and it's going to be a pink, essentially at and above 10. Well, it's said that this turns pink. What we know is that the pH must be greater than 10. We're using that specific indicator. Now, taking a peek over here, you're going to see expressions of 3 different common indicators. Our question is, which of these indicators is best suited to distinguish between a solution that is slightly acidic and one that is slightly basic? So remember that neutral is going to be pH 7. We want to see a color shift right around pH 7. As I look at methyl red, you're going to see we're a bright yellow in the 10 and 9 range, but we start getting a little bit orange into the 7, a much more orange expression at 5, then it becomes red at 4 and stays pretty consistent. So our change range here is going to be closer to pH 5. From thiamyl blue, you'll notice we have our 9 and 10 are essentially the same blue. Between pHs 2, 4, and 5, they're basically the same yellow. And then at pH 7, you have a green solution. So we're seeing our big shift there between the 5 and 9 range. That might make sense for us. Finally, we have phenolphthalein, and our phenolphthalein is clear at pHs 2, 4, 5, 7. It doesn't start at shift. Its light pink is at 9, and at 10 we have our bright pink. So this is nowhere near the neutral pH range. Our best choice would have to be the bromothiamyl blue. So now that you guys have had your content, what we're going to do is we're going to transition, going to shift into some of the practice problems, and we'll get to that in just a sec.